Hi, my name is Pritam Mondol, and I have completed my masters from IIT Kharagpur this year. And this is a demo class for complex number. So let's start with it. We'll be discussing three aspects of complex number. One is one is complex number system. Second one, properties of complex number. And if time permits, we'll also discuss about the magnitude, arguments, and polar representation of complex number. Polar representation of complex number, right? So let's start with the complex number system. From where we get this complex number actually. Basically, we can split this complex number in two halves. Real, like to represent a complex number, we need a real line, and another is a imaginary line. Now we all know what real line is. Real line is basically composed of real number. Real numbers are composed of rationals and irrationals. Rationals, irrationals, dot dot. Right? Uh, Now we'll talk about this imaginary line. From where we get this imaginary line. Imaginary line is basically nothing but the imaginary consist of imaginary numbers. Right? Imaginary number. See, we can solve any linear equations, right? Like ax plus b equal to c. We can solve it, right? Where abc from real number, abc are real number, so we can get the value of x as c minus b by a, right? And this belongs to real number. We can solve this kind of equations x square minus x square minus 4 equal to 0. We get the value as x equal to plus minus 2, right? But can we solve this x square plus 1 equal to 0? Can we solve this and get some real number? Is it possible? It is not actually. Why? Because x, then if we try to solve this, then x equal to or x square equal to minus 1, right? From there we get x equal to plus minus root under minus 1. Now we are talking about real number, right? Now there is no real number exist whose square is in minus. Like there does not exist any real number say r belongs to r such that r square equal to minus 1. There doesn't exist such real number. Doesn't exist. So we cannot find out a real solution. That's why we define iota as root under minus 1. Root under minus 1. Sorry. Iota. So basically I is equal to root under minus 1. And this is called iota. And this is the backbone of the imaginary line. Using it, we define imaginary line. Now, this iota has some properties. We'll come to that, like how we're constructing the complex numbers. there are some properties of iota, right? I equal to root under minus 1, so clearly I square, this is equal to iota into iota, this is minus 1, right? Root of minus 1 into root of minus 1, then we get the whole square, then we get minus 1. Then iota cube, this is equal to, this is equal to iota squared into iota, this is equal to minus iota. Iota to the power 4, this is equal to iota square into iota square, minus 1 into minus 1, which is basically plus 1. So on it will continue like this. We can compute any kind of powers of iota, right? Here is a little question. Can I iota to the power compute iota to the power suppose 12548? How do you compute this? See, 12548, we try to see that whether 4 divides this one or not. 4, it basically 12548, 4 divides 12548, right? And what would be 12548? This is would be 4 into 3 uh, 137, right? So we can write it as I to the power 4 into 3137, and we can write it I to the power 4 into 3137, which is basically 1 to the power 3137, which is basically 1, right? So that's how we compute these things. Now we come to our main point, which is complex number. So basically we find that iota, this value iota is equal to root under minus 1, which don't lie on real axis. So this kind of number, right? So any kind of number root under minus 7, we can represent it as root under minus 1 into 7, right? Which is basically iota into root 7. So basically this kind of numbers, for this kind of numbers we cannot put it on real line, so we define a imaginary line to put these numbers on that line, to put represent it graphically, right? So to put any numbers kind like ib, where b belongs to real number, so to put any number on a line we represent imaginary line or imaginary axis. We define imaginary axis which is not the real line, does not associated with the real line. So in order to place this whole discussion in a more rigorous setting, we will define operations involving combinations of real numbers and imaginary units, and we call this number system complex numbers, right? So we may express an order pair of real number, say AB. Uh, we can express the order pair of real numbers AB as complex number by by defining A plus IB, right? Now, how can we represent this A plus IB in graphically? This is nothing. How do we put this A comma B, this order pair, in a in graphically? How do we represent it? It will be the same. A plus iota B, we can represent it as, suppose as this point, this is the real axis and this is imaginary axis, right? Here will be 1 2 dot 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 minus 1 dot dot dot, and this will be iota into 1, iota into 2 dot dot dot, this way it will be. minus iota into 1 minus iota into 2 dot dot, it will go like this. And suppose that um, this length, suppose here a comma b, obviously from in this a plus I, we try to represent a plus iota beta in a graphical way, right? So a and b belongs to R, so a can be represented on this real line, right? Suppose that this is a, and the b is also from R, b is a length, right? And this imaginary line is nothing but, this is kind of a real line but in a different direction. Real line is horizontal and this imaginary we are representing it at vertically. So suppose that this b length is over there, this iota b, right? Or b, we can simply say that this length is b, so we can represent it this number a plus iota b over here, and this distance is a and this distance will be our b. So that's how we represent any complex number graphically, or on some grid, you can say, right? Now let's look at the properties of complex number. As I have said, that we may express any order pair real number, any order pair of real numbers a b as complex numbers by a plus iota b with some operations, right? So what would be the operations? Suppose a1 comma b1 equal to a2 comma b2, it will imply a1 equal to a2 and b1 equal to b2. A1 comma b1 plus a2 comma b2, this will be a1 plus a2 comma b1 plus b2. uh, a1 comma b1, this is the most important property of the complex number. A1 comma b1 dot, this is not the real, like not the real dot, right? Real multiplication component wise, this is the complex multiplication. A1 comma b1 dot a2 comma b2, this will be equal to a1 a2 minus b1 b2 comma a1 b2 plus a2 b1. Don't worry, I'll show these things, all of this. These two things are very trivial. If we try to prove these three properties using a plus iota b, this representation, these two things are very trivial. I'll show you this third one, right? How this multiplication holds for complex numbers. See, a1 plus iota beta 1 into a2 plus iota beta 2, this is equal to, we simply multiply this one, uh, a1 a2, right? A1 a2 plus iota into a1 b2 plus iota into a2 b1 plus iota square b1 b2, right? And we get, see, iota square means minus 1, right? We have just proved it earlier, we have just shown it earlier, right? So these are the real portions, these are the real numbers, both of them. So we can put it together, a1 a2 minus b1 b2 plus iota into a1 b2 plus a2 b1. See, these are the same. This we can represent at alpha and we can represent it beta, so it will be alpha plus iota beta. It's a complex number, and this is this representation, or this multiplication and this multiplication are same. We can show it, right? There is a little exercise we can do. It's like what would be the, how do you compute iota into 2 minus 3, I suppose. What would be, it's really easy, right? 3 into iota square, iota square is minus 1, basically it gives me 3, and plus iota into 2, it's very easy.